Welcome to Syzygy, episode 4, The Music of the Stars. Welcome back to another episode of Syzygy. It's an exciting week, this one. I don't know if you listened to episode number 3. If you did, you know that we were excited last time as well. We were preparing for the launch of TESS, the Transiting Exoplanet Survey Satellite. But it was sitting on the launch pad when we recorded last time. We didn't know whether it was going to get up. Well, we're here to tell you that it did. And it's in orbit, and it's very exciting. Joining me at the microphone, as ever, is Dr Emily Brunsden. Hi, Emily.
Hello, hello.
So, big week.
Yes, it's been super exciting.
Yeah, so TESS is up in orbit. It's doing its thing.
It didn't explode.
It didn't, right? I'm amazed how exciting it was watching this thing, but how nervous I was. Like, as someone who, the only investment that I've got in this little spacecraft is the fact that I know you and you're excited about it. And I was getting really nervous. Come on, get off the launch pad. Because it could have just been a big fireball.
It could have, but it wasn't.
It wasn't.
And now TESS is the little spacecraft that can.
That's right. We thought when we recorded the last episode, which was last Monday, as we're recording this now, it doesn't matter. We thought that it was going to launch that night, on the Monday night. And then at the last minute, NASA and SpaceX sent out a tweet saying, no, we're backing off from this one. We're not doing it. And it was something technical. I don't know if you know any more about it. But
yeah, something about guidance systems.
Yeah. Which, I mean, frankly, look, if they're not ready to launch something to do with guidance systems, I'm prepared to take their word for it. You know, there's a lot of money and a lot of explosives sitting on that launch pad. If they're not 100% sure that this thing's going to work, fine. You know what? That's okay. So they pushed it back for 48 hours. It launched on Wednesday night, UK time, late Wednesday night, and watching it ready to go, and then up it went. And it's amazing how quickly it goes up as well, isn't it?
Yeah. And it was just so beautiful just watching it on its own little merry journey into space.
But the speed at which it leaves that launch pad. I mean, I know it's a rocket. You know, it's got the equivalent of, I don't know how many large jet engines worth of thrust pouring out the bottom of it, sending it up into the sky. It's going to go quickly. But it doesn't cease to amaze me how fast these things just rocket up into the sky, I guess, hence the name. Yeah.
And it still takes a few days for it to get into its orbit.
Yeah, I mean, it takes minutes for it to leave the atmosphere, but it takes days to get up into orbit because it's a complicated orbit. This is not just sort of getting up into space and going, there you go, you're done. So what's it doing? What's it doing now?
So TESS is now almost finished its kind of orbital maneuver testing. It's done its little jet thrusts and a couple of little burns to make sure everything's tickety-boo in terms of the orbital mechanics. And everything that's been tested so far has worked wonderfully, which is so exciting.
And that's a NASA term, by the way, tickety-boo. That's
yeah.
You know, that's there in their playbook. I like that one. But yeah, I mean, it's got a lot of maneuvering to do in order to get into this very fancy orbit that it's got, which I couldn't even begin to describe. But it's a finely balanced orbit that is inclined to the orbit of the Earth and the Moon.
Yeah, about 40 degrees inclined, and then it sort of comes quite close to the Earth and then goes out just about as far as the Moon itself. So it takes about half the time that the Moon takes to go around.
And why is it in this crazy orbit? Why couldn't we just put it up like all the other satellites that we got up there, just orbiting around the Earth doing its thing?
Well, we don't really want the Earth to interfere, and we want to look away from the sun because we're looking at stars and things that are quite dim. So we don't want to have Earth shine, which is the reflection of the Earth shining back into the telescope. We want to get nice away from that, point away from the sun. And at the same time, we want to have good communication with the satellite, be able to download enormous quantities of data. So when TESS comes close to the Earth, it actually turns itself around. We get the big download, and then when it goes on its merry way out back into space, then it turns around and starts looking at the sky again.
So it's getting ready. It's getting itself into position in orbit at the moment. How long before that's all, as you say, tickety-boo, all those boxes are ticked, right, let's start taking some data?
Well, they've allowed for up to about 2 months to test everything. So you imagine there's a huge number of electronics that are on board the satellite, and they've got to basically turn everything on one thing at a time and then turn it off to make sure everything independently works. And that includes all the cameras that are on board. So
because there's quite a few of those.
There's four cameras that are doing the main observations, and then 2 guide cameras as well. So basically during this period, they're going to switch everything on one thing at a time, make sure it works, turn it off, and then in a few weeks' time, try switching everything on and get into what we call commissioning phase, start taking some really preliminary data, see what works.
You take that preliminary data, you download it, you sift through it, and make sure that it matches what you expect before you start looking at things which are critical to the mission, so that you can be absolutely sure that everything's working.
Yeah, and if there's any really fine adjustments that need to be made.
Nice. So you, when we were casting about for a title for this particular show, and we settled on Music of the Stars, and you said that has a particular resonance with you, that title. Why is that?
Well, the Music of the Stars was the title of my PhD thesis.
Right. So why Music of the Stars? What are we talking about?
So what I look at in my research is I look at stars and I look at how the light from the stars is changing. The reason for the light changing in these stars is what we call an acoustic vibration, or at least some of these changes come from acoustic waves in stars. And acoustic is linked to the same physics that actually sets up music and musical instruments, like a drum.
And when you say acoustic waves, I mean, it's a bit difficult for me to imagine what an acoustic wave, which is talking about sound, with a star. You're not talking about the star sitting up there humming away in space to itself. It's not doing that, is
No, it is physically moving,
right.
But it is physically moving in a kind of similar way to, say, a string on a violin physically moves, the surface of a drum moves up and down. So those physical movements are then interpreted into sound by our ears. We're looking at physical movements that affect the light. And I guess if we really wanted to, we can actually translate that into a sound later on.
I'm sure someone's done that.
Yes,
Someone's got to have done that.
Yeah, we can do that.
The Boston Symphony Orchestra live with star sounds. I'm sure someone's done it. We'll look it up. We'll put it in the show notes. We'll see what we can find. But what has all of this got to do with TESS? Because, again, in the name, it's a transiting exoplanets survey satellite. So it's looking at, as we described last week, incredibly small variations in the light that's coming from stars. When a planet orbiting around that star passes in front of it and blocks out some of that light, and the light from the star dips by a tiny, tiny amount, but we can see it with these very sensitive cameras. So that's what TESS has been sent up as a major part of its mission. What's that got to do with the music of the stars?
Well, of course, planets are exciting and amazing things to study in their own right. But it turns out the way that we detect planets, and this is true for both on the Earth and in these wonderful satellites like TESS, that the same techniques are actually really useful to understand the stars that the planets are going around. And the nature of our observations of planets means that most of the time we only know a limited amount of information. We tend to only know, for example, the ratio of the radius of the planet to the radius of the star.
Right, okay, because if you've got a planet going around a star, and you see the planet go in front of the star and it transits, it blocks out some of that light, what you're saying is that it's very difficult to tell the difference between a small planet very close to a star of a certain size or a large planet fairly far away from a large star. They might look exactly the same,
Exactly.
but you can't tell without further information. All you can tell is relative to the star, the planet's this big.
Yeah, and so you need a bit more information to tell you something about the planet. And one of the ways, actually, very simple things about stars are very, very difficult to measure.
Well, they're a long way away. I mean, fair
a really
enough.
long way away. I mean, we don't look at a star, we can't see it like a disk, like the sun. It's far too far away for that. We just see a tiny pinpoint of light. So we can't measure the radius of a star directly. We have to use some other techniques.
And is that true even for the closest stars, that they are so small in the sky, they're so far away that you literally cannot see its size?
We can't,
directly?
not directly, no. So, yeah, it's really, really hard to work out a very, very basic thing like how big is a star? What is its mass?
So you must be able to get some information about size and mass from brightness.
Yeah.
Big, bright stars.
Yeah, and temperature is also really important.
So the colour of the star as well, because the colour gives you the temperature, doesn't it?
Yep. But these things are quite model dependent. So it means we have to have a good grasp on the physics that we're dealing with. And they might not be super accurate. So we have to think of new ways that we can start to make these measurements. And what we want to do is push that even further and say, okay, well, even if we know we can work out what the radius of a star is, its mass, we want to find out more about the physics of what's really going on inside the star.
Because we do have one star near to us, which we can actually see. We can measure its size and we can look at, not directly, don't do that, kids, that's a really bad idea, but we can look at with special telescopes and instruments in great detail, and that's obviously the sun, right? And it's clear that the sun is not just sitting there unchanging in space. It is varying. It's varying all the time. I mean, in extreme variations, we get solar storms that threaten to wipe out communications across the planet. So it is changing all the time. So the music of the stars that you were talking about, the acoustic waves and so on, small changes in the way that the star's shining that we can measure with very sensitive instruments that tell us about the star.
Yeah, and the wonderful thing about many of these waves is they're not just limited to the surface. So these waves will travel into the interiors of the stars and bring back out with them information about what the interior of a star might look like, which is really rather fascinating.
That is very cool. So okay, before we get onto that, let me just clarify something. We are talking about incredibly small measurements again, aren't we?
Yes.
Because, I mean, when you look at stars, and I know astronomy is not just going out into the field and looking up and, stars. But when you look at them, they seem constant. You know, they might twinkle because of the light coming through the atmosphere, but the starlight is incredibly constant. What kind of level of variation are we talking about here? Like percent?
Well, even more than that in some cases. But it's we started off when we started looking at variable stars. We started off, of course, with the most obvious ones. And some of the biggest stars that vary of their own accord are Syzygy, which are very famous. They have big pulsations and they change quite a lot in brightness. Some of them are even observable in changes if you can measure the brightness compared to stars around them.
Right. On what kind of timescale? Are they pulsing on and off?
Cepheids are a few days.
Right.
So they've been known about for hundreds of years, these brightness changes in these stars. And actually, it's the same with all types of pulsating stars. We kind of found the most obvious ones first, and we go for the biggest pulsations first. But now we're down to the point where we need to have very, very precise measurements. So these are things in millimagnitudes or millionths of a unit of brightness. So fractions of a percent again. And that turns out to be exactly what the planet hunters are after as well. Because
if you're looking for these transiting exoplanets, you're looking at fractions of a percent. And so all the astroseismologists jumping on board going, so while you're looking, could you just throw us a pile of data as well? It's perfect.
Yeah, and by the way, we can help you out a little bit with some of your planets and give you some masses and radiuses of the stars they're going around.
Do those things interfere with each other? Does the fact that stars are variable, and I'm assuming, at some level, all stars are variable. None of them are just sitting there doing nothing. So does the variability of stars hurt your ability or astronomers' ability to find exoplanets? Because you're looking at the same kind of level of variation. Do people ever think, oh, look, there's an exoplanet? No, it's just the star burping. Do you get that kind of thing?
For the kind of pulsations that we study, not so much, because they're very regular. So if you can imagine what a sinusoidal wave looks like, so a sine or cosine or any kind of just wave that goes up and down and up and down and up and down all the time, that's happening all the time throughout the stars, the observation period that you're looking at the star. The timescale can be minutes, it can be hours, it can even be days or weeks, but basically that time period
very regular.
is happening all the time. Yeah.
Right. Which
up,
is
down, up,
not
down.
the same with a transiting planet. It'll whip across and then it's done, and it's a long time before it comes back around again to do that blip.
Yeah. So
You know,
the shape...
the blips are regular, but the shape is not a sine type wave, you know, your classic wave up and down.
Yeah, you just get a blip and then you have to wait until it happens again.
Right. So they're relatively easy to separate out, those two signals.
Yeah.
Right.
Yeah.
Okay, cool. So backing up to what you were just saying a minute ago then, what can you learn from the music of the stars, from these waves, these oscillations, these vibrations? What can you learn about the structure of the star? What can they tell us?
Well, we don't have any way in which we can send like a space probe or something like that into the interior of a star and say, oh, what's going on here?
I mean, that would be cool, but engineering nightmare.
Yeah, I mean, the temperatures, the pressures, and even forget the distance, right?
What are the temperatures? The surface of the sun is...
well, the surface is only a few thousand degrees.
Only a few thousand.
But you're getting into millions pretty quickly by the time you head down into the interior.
Yeah, I don't know that we'll be doing that anytime soon. So we can't stick a probe literally into the sun and measure, you know, are you done? Are you baked? But we can infer stuff through these observations. So what sort of stuff can we infer?
So we're looking for very specifically densities, and we're looking for where do the waves travel to inside the star, and how where is the core. So the core of a star is this very, very interior part where you have the fusion reactions are happening that are powering the entire star.
Right, because that's only happening right down, as you say, right down in the core, isn't it?
Yes.
Where the temperatures and the pressures are so extreme that it's forcing these atoms together. It's forcing hydrogen together to make helium and so on. It's not happening around actually most of the star itself, is it? The outer layers.
No, it's only happening right in the core, yeah. So we want to ask the questions, well, how does fusion work? Then we need to understand how big is the core, therefore, you know, what temperatures and pressures is it going to be? How is energy transported out from the center of the star out to the surface? Where are the blocks in that process, if you like?
How do you get that kind of information from looking at small, tiny variations in the... I have a feeling this podcast is going to have me saying this sort of thing a lot. How the hell do you do that?
So the wonderful thing about the waves that are traveling in the interior of the star is that how those waves are formed, so particularly the frequencies of those waves, is dependent on the medium through which they're traveling through. So what a really good measurement we can make is, for example, what is the speed of sound inside the star?
Speed of sound being how fast does a wave travel through a particular medium. So you know, the speed of sound in air depends on the temperature and the density of the air. Speed of sound through solid objects like, you know, a wooden table or something is much faster because the table is much more dense. So you're able to infer similar properties about the material that the star's made out of by how, or, you know, be able to tell how fast those vibrations are going through it.
Exactly,
Wow.
yeah. And then those frequencies are what we measure on the surface as how fast these waves are moving on the surface of the star.
So I'm guessing you're seeing lots of different waves. It's not just a single, you know, vibration. You're seeing lots and lots of different things sort of on top of each other. Waves going around the surface, waves going through the middle, bouncing off the core, that kind of thing.
Just about, yeah. So
it sounds really similar to the seismology here on Earth. That you know, when there's an earthquake on the other side of the planet, you get waves going across the surface of the planet, you know, literally as water waves, but also waves across the land and stuff as well. And you can detect that a long, long way away. But you also get waves traveling through the planet, ricocheting off the core, bending around through different layers of material and so on. So it's the same kind of idea. It's
exactly,
the same...
yeah. So it's no coincidence. It's called astroseismology, right?
I guess it makes sense. I've only just put that together. I mean, I was down... we're recording this here in York, and I was down by the river the other day, and there were some geologists, seismologists, maybe, I don't know, and they had a big rig where they drilled down beside the river here in York, and they were doing some acoustic soundings. And so as I was running past, I was out for a jog. As I was running past, there were these huge booms that were coming up out of the ground, and I could actually feel it kind of, you know, move my feet, push against my feet as I ran past. It was doing that every 10 seconds or so. And I'm assuming that they're doing that in order to send these waves off into the ground to be able to tell what's down there. because you can then measure how quickly did that wave bounce back, what direction did it come from, how strong was that wave bouncing back. It's all the same stuff. You're just doing that from a distance of, I don't know how many light years away, on tiny pinpricks of light in the sky.
Yeah.
So points to you. Well done.
Well, unfortunately, we don't have the luxury of going and setting off our own booms. So we just kind of have to wait for look for particular stars that are doing it themselves, basically.
So what sort of things are you most looking forward to? You personally, Emily, what are you looking forward to seeing in this data? What are you hoping that you're going to be able to explore?
So my aspect of astroseismology is I'm actually usually working with ground-based data. So I use a slightly different technique to what Tess is doing, for example, where I study the colours of the lights of the stars changing. And that tells you just a fraction more information, actually, than just the frequencies. You can actually start to lay down the geometry of what the star's pulsation looks like.
When you say the geometry, what do you mean by that?
So these stars are not sort of going in and out like a breath or a lung expanding and contracting. They have what we call non-radial pulsations, which means parts of the star are sort of coming out, other parts are going in. It's all symmetric. So a very simple example would be the segments of an orange. So if you cut an orange into quarters, then you could have 2 of those quarters moving out and 2 moving in. That would be what we call a mode of pulsation. And if you had you cut into 6, or if you cut it into 8, and if you cut it lengthways as well, through the middle as well as along the core, then you get different geometries.
So all these different kinds of vibrations that you can set up in a 3D object. It's a little bit like harmonics on a guitar string. You've got the main way that the string vibrates, and that gives you the main note. But then there's all these other harmonics that you can get by just touching along the string in different ways. And there's different ways for that particular string to vibrate. But that's just along one dimension. In 3 dimensions, that's much more complicated. You get much more interesting shapes.
Yeah. So you get these nice, it's almost like segments of the star moving in and out in phase, so that it all sort of looks nice and symmetric.
Why does it do that?
So, it's to do with the interior properties of the star. Turns out when you get to a certain range of temperatures and pressures of a star, then they kind of self-excite these oscillations themselves from the interior mostly, and then they propagate out through the star itself.
Same idea as getting back to the guitar again. I've got a guitar hanging on the wall of my house, and when my 12-year-old slams a door somewhere, which she's wont to do, that slamming will lead to my guitar ringing on the wall. It'll just sit there and ring at its particular frequency. So are you saying that the energy in the star is exciting its own ringtones, if you like?
Yes, yeah.
But because there's lots of different ones of those, it could be doing all sorts of different things.
Yeah, and you often see lots and lots of different pulsations overlaid on top of each other, and that can get a bit complicated.
Yeah, well, it just gives you something interesting to analyse in the data.
Oh, of course. Complicated is a good thing, right?
So what can that tell you about the star? What are you learning from that, other than, hey, this star's ringing at a frequency of whatever?
Well, we can actually apply that to our models of how stars actually work. Now, I have to be a little bit of a confessionist here and say our theoretical models, like we can construct a computer simulation, for example, of how a star works, are actually reasonably primitive. So we've got some basic physics we can put in there, but for the most part, we can only model a star maybe in 2 dimensions if we're very lucky.
Any stellar astrophysicists out there who are taking issue with this description of the state of the art, you can email Emily, not me. It's not,
No, it's wonderful work, but it's hard stuff, right? Stars are really hard.
Well, particularly as they're a long way away, and we can't send something in to measure what's going on. You've got to infer everything.
Yeah, and this is sort of plasma science that's well beyond what we are generally creating in laboratories on Earth, and certainly on scales that we don't create on Earth. So stellar models are really hard. And what we're trying to do is improve those by adding in the constraints that we have from observations. So if we can say, actually, we've observed this group of stars that behave like this, we can input that into stellar models. It can really tighten up some of the known physics that we have in there and tell us something about the fudge factors that we've had to add in to make them work that we think might be real, but we're not 100% sure.
I'm guessing it's also the case the reason why TESS is so exciting is because, at one point we had one star that we could look at and measure really well, which is the sun. But that's an N of one. And anyone who knows anything about statistics knows that having one data point doesn't really tell you anything about stars in general. And then we started seeing or being able to measure more stars, but not that many. And when the Kepler satellite went up, I'm guessing that it was also used in the same way. And that gave us thousands. But TESS is going to take it up another notch, and we're going to get lots and lots of data of nearby stars. That's the thing about TESS, isn't it? They're nearby.
Yeah. So if we sort of think a little bit progression-wise, well, some of these things kind of happen simultaneously, but we've now worked out that we know, for example, how fast the core of the sun rotates, which is a pretty amazing thing on its own. I mean, we've just by looking at the surface of the sun and measuring these pulsations, we've been able to work out that the core of the sun is rotating something like nearly 4 times faster than the surface.
Wow, really?
Yeah, it's really incredible.
That's amazing. So there must be all sorts of incredible turbulence going on inside there.
Yeah, the stars are basically a hot mess.
Wow, okay. But that's something we've only just learned about our closest star that we've been observing in high detail for decades.
Yeah.
This is hard stuff.
And now from Kepler was one of the areas it was so successful was with red giant stars. And these are basically the next step on in the evolution of a star after the sun.
Red giants. So towards the end of a star's life, it's running out of hydrogen, so it starts to have to burn helium, and it starts to expand. It gets bigger. It gets a lot bigger.
So the clue's a little bit in the name.
Giant. Yeah, I mean, I could have got there about 20 seconds ago, but yes, I mean, it gets. But it's to do with it running out of the hydrogen fuel in the core and kicking over into having to burn different kinds of nuclear fuel, right?
Yeah, so these stars sort of blow up to maybe 100 times what they were when they were like the sun, merely fusing hydrogen away to helium. And there's 2 different processes that are really interesting in red giants. The first one is basically as the star starts to run out of hydrogen, it's dumped all the helium into the center. So it starts to fuse hydrogen in a kind of a shell around the core. That can go on for a while, but it does actually run out of hydrogen there as well. And so there's an ignition point where helium starts to fuse. Now, these are all really deep down inside the cores of stars. So we think, well, we can never really observe, from the surface of a star how that change is happening. But with astroseismology, we've been able to determine the ages of these stars so accurately that we can now say what part of this helium fusion or hydrogen fusion process that they are at in their lives.
Wow. That's amazing.
And then, of course, we've also been able to measure for now hundreds of stars the rotation rates of the cores, particularly with these red giants. We've been so successful. We know so much more about red giant stars from Kepler than we even dared to dream that we might know.
So all of this new data that you're pulling in from Kepler and soon from TESS, you're going to be able to feed that back into the physics models and the simulations to say, well, okay, all of those things that we had to fudge before, throw in a number because we just don't understand this. We now understand it a lot better. So you can now work that through in your models to understand the physics better. And you get that nice cycle of... Yeah,
we're getting better. What we want to do is create a picture of a star's life, all the way from when it's born to the end point. So we have some examples of some stars who are just forming. They're called pre-main sequence, so they're just early born stars. Some stars like the sun. Now, we're not so good, actually, at the astroseismology of those ones. I study stars that are in this normal sort of main part of their lifetimes. They're a little bit hotter than the sun because they have to have these big pulsations that we can see. But, primarily they are just a bit like the sun, just a bit bigger, a bit hotter. We're not very good at those ones yet. We're quite good at the red giants. We know quite a lot about them, so that's the next stage on from that. And we're also incredibly good at doing astroseismology on white dwarf stars, which are the very, very end points of stellar evolution. So basically the last little lump of core that gets left at the end of a star's life is called a white dwarf, and we can do astroseismology with them very, very well. So it's like a big jigsaw puzzle of a star's life, and we're putting in bits as we go along, but we've still got quite a few gaps that we want to fill in.
That's all we've got time for in this episode number 4 of Syzygy, the music of the stars. If you've enjoyed what you've listened to today, then let us know. You can get in touch with us and tell us what you've enjoyed, what you want to hear about on future episodes. You can give us some feedback. You know what would be even better is if you have enjoyed it, go and leave us a review. Give us some stars, something like that, on your podcast directory of choice. Go and find us and leave us a review so that other people can find it and share the awesomeness of astronomy with us here on Syzygy.
I really like stars.
Yeah, it's true. She does. She's not kidding around here. If you do want to contact us, there are a couple of ways you can do that. How can they do that, Emily?
Well, we've got our fabulous Twitter account, which has been updating actually really nicely with some of the updates from Tess. So if you want to keep following that story via Syzygy Podcast, it's at Syzygy Pod, SYGYZY Pod. And
I think it's the other way around. SYZYGY Pod.
That's what I said.
No, you didn't.
I definitely said that.
All right, we're going to have to call that on the tape. Go back and have a listen to it again. So at SYZYGY Pod.
Pod.
Yeah, yeah, because we're putting all sorts of stuff up on there, both linked to each of the shows that we're doing, but also other stuff that comes up in the world of astronomy and space and rockets being launched and things like that. Things that we find cool.
Yeah, just geeking out, basically.
Yeah. You can also go to our website, which is syzygy.fm. We're going to be back again sometime within the next week or so because we've got another story that we really want to talk about. There's been diamonds in meteorites, and that tells us about the history and evolution of the solar system. How cool is that?
Diamonds falling from the sky. You've got to be lucky to get one of them.
I think these diamonds are really small. I don't know. I'm going to have to go and read the paper again, but we're talking nano diamonds here. Still, diamonds in meteorites. Can't get any better than that. So come back again for episode number 5. That's going to be really cool. We'll catch you next time. See you later.
Goodbye.
What can you learn from the music about... We'll come back to this question in just a second.
It is off the hook.
Oh, ghost phone calls. Let's try that one again.
Yeah.